recording the session. We have been observing the system and hoping that we will not miss any force vector or torque or anything, any spring, gravitational field, whatever. So we have to accommodate everything and be very careful with projecting forces on the proper axis and so on. So writing the equations of motion just from your mind, from guessing, requires certain perseverance. And there is a simpler way to do that, and it's very general. So I would ask you to pay close attention to what is going on here. It's kind of complicated stuff from the first glance, but it's all will make sense later. So let us consider the following function. It will be called Lagrangian, after a mathematician, Lagrange. It was his family name. And this Lagrangian for a system is kinetic energy minus potential energy for some reason, for no apparent reason, basically. The potential energy is denoted as T. I'm just checking if you can see the writing. You can. Maybe I'll add some lights. Hold on.
It's clear, actually.
Okay. Anyways, that's is better. Okay, so you can see the writing. Great. And are you familiar with partial differential equations? So you know that you can differentiate functions by different arguments, right? So you can do that.
Yeah.
Yeah. So what I'm stating is that we can use this Lagrangian to obtain the equations of motion using a certain general formula with partial differential equations. So at first, we are not going to consider any specific system. It will be just a system, and it will have so-called generalized coordinates. A generalized coordinate is, it will be for us one of two types of coordinates. The first coordinate is the translational or linear coordinate, and the second is rotational. In the robots, we really have those two and nothing more than that. So we have prismatic joints. I mean, I don't have any because I'm a human. So we have prismatic joints and we have rotational joints. Okay, sure. Be back soon. We'll be developing this. So I will denote these generalized coordinates by Q sub I, where I is 1, 2, n, if the system is n-dimensional. For some certain cases, like an inverted pendulum, it will be just 1. So we will have just one generalized coordinate. But we can assume the system to have n of them, and it's all will be fine. If we have n generalized coordinates in the system, it will result in n equations of motion. So the kinetic energy will probably incorporate something along the lines of Q sub I dot. In the case of a moving particle, it will be m/2 v squared. So let's consider an example just right away. This is a moving particle along the axis, just one mass over here, and our state vector is composed of x and x dot. So we have only one generalized coordinate. Let's choose a different name, actually. Let it be m. Oh, no. Let it be k. Sorry for that. So let it be 1 through k. And here k is equal to 1. So we have one generalized coordinate. Well, we will expect just one differential equation. And the kinetic energy here will be simply m times v squared over 2, which in terms of the generalized coordinate x will be equal to m x dot square over 2. Is it fine so far? Is it okay?
Yeah. Mm-hmm.
Great. So this is the kinetic energy. And regarding the potential energy, there is none really, because the potential energy of this thing doesn't depend on x. Anyway, the surface is flat. I mean, the line is flat. So the potential energy here is just 0.
The
And
potential
the,
energy depends on height, right?
yeah, it depends on the height, but the height doesn't change. So we can arbitrarily set this level to be height equal to 0 and nothing will
Yeah,
change. I
yeah.
mean, yeah. So we don't change the height. It doesn't depend on x anyhow. And this potential energy could be equal to just 0. It's for simplicity. If it's a certain constant, nothing will change. We'll show that in a second. So the kinetic energy usually depends on the q sub I dot. Well, this is just the derivative by time of q. So q dot sub I is d by dt of q sub I. This is the denotion. And the potential energy usually depends on q i's without dots. So what could this mean really? If we would have a two-dimensional particle, it will be, okay, so this, and here it will be y dot square, and the potential energy here will be m times g times y. Okay, yeah, I have to amplify, extend this vector, y dot, and k will be equal to 2. That's fine?
Yeah.
Okay, great.
I was
So,
about to ask if we
yeah,
added an axis, would the K changes or not? But yeah.
yeah, yes, yes, it
Mhm.
does. So, it's, I will draw this point over here, or it's this brick. I mean, we don't consider the rotation, but I'm saying that it could be on any height and any horizontal coordinate. So the kinetic energy is just this thing, and the potential energy depends only on the height. So my statement is that we can use this Lagrangian, this thing that is equal to kinetic energy minus potential energy, to derive the equations of motion of this system. And the form in which we are going to obtain that is the following: d by dt of a partial derivative of the Lagrangian by the derivative of the generalized coordinate number I, sub I, minus partial L partial Q sub I. It is equal to 0. And we're going to have this for I equal 1 and 2. This is the formula that we are going to use today. And it's very fundamental. So we'll spend some time talking about this. Don't worry, it will be all good.
I think I took it in a course called in the PDA course.
Yeah, PD. So
Mm.
it was a
Partial,
second year,
partial,
I guess,
partial.
or third year.
Third year, third year.
Third year. Yeah,
Hmm.
that makes sense.
Maybe even fourth year. No,
Yeah, so
third year.
yeah,
Yeah,
we have that on the third year as well.
yeah, yeah.
Or
Same
we
here.
have it in theoretical mechanics, and we have a separate course on PDEs, during the third year. So yeah, there's a so-called Euler-Lagrange equations, and
Mm-hmm.
we can write down such an equation for each of the generalized coordinates. For such a system, for a particle, we have two generalized coordinates, which are x and y, and using this Euler-Lagrange equation in general form for different generalized coordinates, we can obtain the equations of motion for this object. So let's do it. I'm going to do it over here and then continue over there. And you can follow me if you feel like doing so, or I'm going to just clearly explain everything, and you can ask questions. Please do that if something is not clear. So first I'm going to obtain the equation of motion with q sub 1. Q sub 1 is the first generalized coordinate, which is x. So I'm going to write down d by dt of a partial of the Lagrangian. Okay, let me write down the Lagrangian first, just explicitly. So Lagrangian is equal to m x dot square plus y dot square over 2 minus m g y. And now I'm going to take partial derivative of this Lagrangian by the q sub I, which is x dot. So partial derivative of the Lagrangian by the x dot will be equal to just m times x dot. Why so? Because the second term here doesn't depend on x dot, and this thing doesn't depend on x dot as well. So we have to take only m x dot square over 2 and differentiate that. And what we get is we get 2 here, so they're getting canceled. And we finally obtain m x dot. And after that, if we're going to take the derivative by time of this thing, we will result in m, because m is a constant, x double dot. X double dot is the acceleration. Is it all good up to this
Yeah,
point?
all clear.
Great.
Yes, yes.
So yeah, and the last part is just the partial derivative of the Lagrangian by just x, by x1. But the Lagrangian doesn't depend on x, so partial L partial x is 0. And the first equation of motion is the following. M x double dot is 0. What does it mean? It means that if we throw an object somewhere, its horizontal velocity will not change. It's a pretty obvious observation, but still, I mean, we just got it from this formula. This observation is, I mean, it corresponds to the intuition. It's working. I'm not going to prove this thing. I'm just showing how to work with this and how to interpret our observations. And with the second generalized coordinate, we're going to have this situation a bit more complicated, but it will be just very simple, and it will be in line with our expectations. So regarding partial L by the y dot, it will be the same, but here we'll have y. After differentiating by time again, we will get the following: d by dt dl by dy dot will be equal to m y double dot. That's fine for now. And now let us take partial derivative of the Lagrangian by the second generalized coordinate, which is y. And here we are going to get just minus m times g. Okay, so let's write down the second equation of motion. It will be m y double dot minus m g equal to 0. So from here we can say that x double dot is equal to 0. And from here we can say that y double dot is equal to g. I hope that you will not confuse my handwritten g with 9, but yeah, I mean, it's close, at least. I mean, to 9.8. There's a joke going around that pi square is almost equal to g, the gravitation constant. So yeah, what do we get here basically? Here we get the pretty simple thing that the horizontal velocity will not change since the second derivative is 0, and the first derivative, the second derivative of y is just g. So if we let me take another marker. Hold on. I have got 2 markers. That's better. Okay, so I'm going to write some simple observation here regarding the first equation. If we're going to integrate that, we'll have that x dot is equal to some constant, and x double x without any dots will be equal to some constant times t, where t is time, plus some another constant. We will have to determine these constants from the initial conditions, where we are throwing the ball and what's its initial velocity. And with this one, we're going to have a pretty similar thing here. We're going to have y dot is equal to g times t plus constant, and y will be equal to g times t square over 2 plus constant 1 times t plus constant 2, or it's better to call them constant 3. Let me do it properly. So c3 and c4. Is it all good?
Yes.
Okay. So do you feel like doing some derivations by yourself for a pendulum using this method?
We might try out.
Okay, there's a question. How did you get it? Again, the last part with this part or here? Okay, so I will assume that the question is about the very last part, this one. What we have here is the differential equation that says y double dot is equal to g. G is a constant. I'm going to integrate this differential equation, and what I will get is y dot instead of y double dot. So I'm going to do it like this. I will integrate. This is an, what's the English improper integral? Yep.
Integral. So you're using separation of variables.
I mean improper. Yeah, I know that it's integral for sure, but improper, is it the right word in English? So it's improper. I mean, without limits. Am I right?
Mm-hmm.
Yeah. Okay. Thanks. So yeah, get it. Okay, so we do that. We do the improper integral. We get g times t and some constant over here. Then we do it just once more, and then we get this formula for just a parabola. And we get it using this Lagrangian formalism. We don't know anything. We don't have any intuition about what's the parabola and what's going on, basically. So the sheer magnitude of the power of this approach relies on us skipping the tedious inspection of the system. We don't have to write any, we don't have to find any smart projections on some, I don't know, moving system of coordinates, nothing like that. We are just dealing with the balance of the energies, and that's it. So if we are dealing with a simple pendulum, we can do it by, looking at the system. It will work out pretty much. However, if we are working with, let's say, a cart on a pole, this is the classical system and control, something like this, and this joint is not actuated, and here we can apply forces to the side, to the right and to the left. It will be a huge pain to try to write down the exact values of the reaction forces over here. It's a stuff. And if we add another joint over here, can you imagine the pain of trying to write down the exact equations of motion for this system? There are some reaction forces from this thing, uh, from this bar, from this bar. They're acting on this mass. And imagine if the mass is distributed through the pole. So it's a huge pain. And in order to avoid that, we will have to incorporate Lagrangian analysis and Lagrangian formalism into what we're doing with these systems. So is it okay? Do you get the intention behind all this thing?
Yes, somehow.
Yeah,
So basically, we'll find the kinetic energy and the potential energy for the pendulum,
yes,
then put it in the use it as the Lagrangian, and then find the
yes,
equation of motion.
yes, exactly. We don't have to figure out anything directly by observing stuff. We cannot miss it. We cannot miss anything because, well, if we will not miss the formulas for kinetic and potential energy, and they are pretty straightforward in terms of these generalized coordinates. They are usually simple because stuff can rotate, stuff can move. That's it. Uh, so, yeah, there's a question. So is it a better method instead of fighting forces? Yes, exactly. Exactly. Our robots and other complicated robots that are composed of multiple rigid bodies, they're very difficult to analyze. And you cannot really find the exact values of the forces just by observing the system. Because imagine if the robot is standing on the carpet and one of its pressure sensors, it's more in the carpet than another one. So either we have to derive the counteracting forces that act upon the robot's foot, or we can just assume this field to have some rigidity. I mean, Hooke's law of this simple stuff. So it's much better. It's faster. It's easier to use for more complicated systems. And there is a complete proof that it's a valid method to go with. So I'm not going to provide that. I cannot really think of that just now from my head, but you can check, I don't know, Wikipedia or some textbook in analytical mechanics, Lagrangian mechanics. It could be found there. So yeah, when do we need to describe the systems actually? We need to properly describe our systems if we are trying to move the system to a desired state or to move the system along the desired trajectory. So if we're going to control the robots, and we will have to at first formulate their dynamics properly. And the first component of the dynamics is just the state space description. So what's the state space? What's the control space? What are the dimensions? And second, we will have to properly write down all the equations of motion. And Lagrangian mechanics, Lagrangian formalism will allow us to do that. So we're going to use it. What I propose to do, if you feel like doing that, I will write down just the main formulas, and we're going to spend some time deriving the equation of motion for a pendulum. And after that, I'm going to do the same. So the results that you will get should match with the expectations and with the formula for the motion of inverted of a pendulum that you already know. So we'll check this method on a system that we are already familiar with, and then we're going to proceed to some more sophisticated systems, like maybe cart pole or two pendulums or two pendulums with a spring, so something more complicated. And finally, we need all of that in order to proceed to controlling complex systems. So the formula goes, yeah,
I
here's
think
a, huh?
check the chat, please.
Yeah.
Yeah.
What course do you recommend we take our exercises to practice modeling systems with Newtonian and Lagrangian mechanics? Any links like from YouTube or any website? Let me think of that. I'll send some links. Let me write it down, not to forget doing that. So I'll send some links. And another thing, we will have some experience just here. So on a minimal required level, it will be fine just by visiting the seminars and doing the home assignments. So I'll just name some systems, and I will ask you to do the derivation in a week. Yeah, let me write down that I have to share some materials. Yeah, and on YouTube, you can find that on YouTube as well. So I'll check YouTube and some resources. It will be fine. This thing is present in internet. It's not like anything understandable. It's pretty common. It's fine. So there are materials. You'll be totally fine with this in short time. So kinetic potential and q sub I is a generalized coordinate. I runs from 1 through k. I'm going to denote it like this. And for each of the generalized coordinates, the following is going to hold. By dt L partial q sub I dot minus partial L partial q is equal to 0. So this is the general stuff. And I would ask you to derive the equations of motion for a simple pendulum. So the coordinates will be the following. This will be theta, nothing special. So vector x, just for clarity, is theta dot from R2, no control, nothing. Length L, condensed mass small m, gravitational field. I think it's enough. So let us try to obtain the equation of motion, the differential equation of motion of this thing.
Can I consider Q as or X bar as X and Y? Like, can I represent this system as X and Y?
You can do that, but the problem is the problem with such representation is that we have a constraint. So x and y here are not independent. There is a holonomic constraint. There's a constraint that the mass is strictly on the distance L from the pivot, from the joint. And
Yeah.
in reality, it means that we have not two coordinates, but one coordinate. So if we're going a bit off the road, we can say the following. We could have, if we are considering systems on a plane, so plane R2, let us suppose that we have A particles. If we have A particles, we have A times 2 coordinates, if there are no constraints. And then we will have to subtract the number of constraints. Here we have one constraint that says that the square root of the sum of x and y is equal exactly to L if 0 is here. So in our case, the number of particles is 1. It will be 1 times 2 minus 1 constraint. And this 1 will be the number of generalized coordinates in such a system. So there will be just one generalized coordinate, which is which could be chosen to be the angle. Basically, we can choose x, but x will be not as handy in, say, deriving the potential energy,
It
because
won't describe the system, right? Correct.
hmm?
Like, it won't describe the whole like, specifications of the system somehow.
uh, well, yeah, indeed, it won't, but it can. So that's a good question. That's a good point. Actually, it could if the pendulum is not swinging more than 90 degrees. Like if it's not swinging more than to the horizontal position. If it's swinging from this position to this position and not more, then x corresponds 1-to-1 to the angle, and it's fine. So we can use the generalized coordinate x. It will be just not convenient for us to write the potential energy in terms of that coordinate. We can do that, but I mean, here, if we're considering x to be our generalized coordinate, we will have to calculate the opposite side of the triangle. So it could work out. It will work out. Basically, it's
I see.
equivalent, but just here it's more convenient for us, and it's more
Yes.
intuitive. So I prefer to use the angle for pendulums. It really makes sense to do that. There are certain intuitions on where and when use parameterizations. I think we will consider a spherical pendulum. So sorry, there it will make sense to use phi and theta, so two angles. and we'll get all the potential and kinetic energies pretty straightforwardly. How did you know the constraints? The constraints, we'll have to basically check what is the system that we are dealing with. So if there's no bar over here, we have a free particle, and it goes like this. So the number of particles times the dimensionality of the space. If we have no constraints in R3, and if we have, let's say, I'm going to take some objects. Hold on. So this is the best example I can think of. We have, let us have one object. So it lives in R3. I'm not going to consider the rotations of this ball. It's just moving linearly. It has 3 directions to go. So I can describe this ball by 3 generalized coordinates, and there are no constraints. And if I have 3 particles, it will be just the number of particles, 3 times 3, which will result in 9 generalized coordinates. And for each of the generalized coordinates, I'm going to have the derivative of the generalized coordinate. So the dimensionality of the dynamical system will be 3 times 3 times 2, 18. And speaking of the constraints, we'll have to examine the system basically and subtract the number of constraints from the whole number of degrees of freedom of the system. Okay, so can we now derive the equation of motion for this system?
Yes.
Okay, great. So let's spend some time. I mean, you can do that, right? Is it fine?
Yeah, sure. We'll try.
Yeah, okay. I'll get some water. I'll be back.
Take your time. I have a question. In
Mhm.
the kinetic energy equation, which is half mv squared, instead of v, should I put the theta dot?
Uh, I would put theta dot times L. So
Yeah, yeah, yeah.
yeah,
Okay.
yeah, so both squared, of course.
Yeah, of course, because it's the value of the velocity, actually.
Yes, right.
Okay.
And the rest of the logic goes the same. So you'll have to differentiate by theta dot and by theta.
Yeah, yeah. Thank you.
Sure. Guys, we are almost approaching the time limit for today. So what I propose to do is I will go just slightly beyond the time limit, if it's fine. I'm going to show the derivation for this system, and then I'm going to propose a different system for you to work on at home. Is it
Yeah,
okay?
sure,
Okay,
yeah.
so let us write down the Lagrangian here, and it will be m L square theta dot square over 2. This is the kinetic energy minus the potential energy, and here comes the trick. So keep an eye on that. If we clearly the potential energy depends on the cosine of theta. So
Yeah,
the potential energy is at its minimum when the cosine is 1. So the potential energy could be written down as minus m g l cosine theta. And the thing is that we're subtracting the potential energy over here. I can miss this sign from time to time, so I'm just saying that keep an eye on that. The potential energy is supposed to increase as we raise our object higher. So just saying, just to save you some debugging or whatever it is called in the formulas. So it will be mjl times cosine theta. And since we have a single degree of freedom, or not really, we have 2 degrees of freedom, we have one constraint, so we have one generalized coordinate. And let's proceed to obtaining a single equation of motion here. And it will just beautifully converge to what we expect. So dl by d theta dot is equal to m L square. The constant is not going anywhere, it's just a constant. Theta dot. So if I'm going to add d by dt here, just to save some time and space, it will be ml square theta double dot. And now we have to get this thing. And here it gets more interesting because this theta is under the cosine. Let's write it down. So dl by d theta is equal to mgl. The constant is the same, and the derivative of the cosine is minus sine. So here here we have minus, and here mg. And here we have sine theta. And now let's write down the equation of motion. So it will be m L square theta double dot minus this thing, so plus m j L sinus theta. And I'm going to cancel out the mass. I'm going to cancel out the length here and the length of the pendulum, the second power here. And finally, we come to the following differential equation. Theta double dot is equal to minus G over L sinus theta, which is a non-linearized, full, normal differential equation of motion for a simple pendulum, which we have got using the Lagrangian formalism. And we did not use any observations like, let me guess the form of the answer, nothing like that. Just we were using the formal derivation. The only thing that needed our observation and intuition about the system is the number of constraints, but it's pretty straightforward. So once we've described the system properly, we can get the formulas for potential and kinetic energy. And this will give us the exact differential equations of motion of the system. And here comes the home assignment. So let's consider a different pendulum. It will be a pendulum with a spring. Here's the mass. And well, we have the gravitational force, but it's not doing anything. So let's skip that. And this mass is attached to the wall with a spring with a stiffness K. So x-axis is going there. And you can assume that we have a rod, frictionless rod or something. So this mass is clearly going only to the right, left and to the right, nothing more than that. So I would ask you to derive the equation of motion for this pendulum. And
What about the surface?
the surface, it's frictionless. So
Okay.
yeah, frictionless surface, nothing is dissipating, nothing is changing. We will have a look at dissipation and those the trajectories in the phase space that we'll get with different dissipation later at a certain point. So now we are just dealing with the equations of motion. And this is the first part. And the second, if it will be fine, so try to do that. I think it's doable. What I propose to do is the following system. So there are two pendulums. And each of them has the same length, the same mass. We have the same gravity. And well, basically they have two different angles, theta 1 and theta 2. And they're attached to each other with a spring with stiffness K. Stiffness K means basically that F that is exerted to the endpoints of the spring is equal to minus K delta L, where here is the enlargement, or how do you call it? I mean, the change in the length of the spring, basically. So it's a normal basic spring with the Hooke's law. You can, using some force with your hands, you can move these two pendulums apart. You can bring them closer. But if you let them swing freely, they will perform some oscillations. Maybe they will swing synchronously, or they can swing like this, so we don't really know. Let's analyze that. And you can do it using the same formalism. The only difference is that here we have two independent generalized coordinates. So you are going to obtain two differential equations. You will have to write down this thing for Q1 and Q2, for theta1 basically and theta2. But the rest of the logic is the following. And the problem will be solved when you're going to get two different differential equations for the angles.
Okay, that's clear.
Okay, great. So thank you
Can you
for
can you
coming.
take a picture
Yeah,
of the board and
what?
then send it? Can you
The
take a
picture.
picture of
Yeah,
the board?
sure. Yes, of course. Sure, I'll do that.
Yeah, but from your side, so the picture will be clear.
Yeah. I'll take a photo with my phone.
Thank you. And
Sure.
lastly, can you please explain how did you get the potential energy, the
The
MGL?
yeah, sure. There's a question. How can we view the recording? We're going to share them over YouTube, so they're all on our YouTube channel. I've shared that in the WhatsApp chat, so you can search for that. I think I've done that last week. Or if you will not find that, I will send it again. So they're just publicly available. Couldn't find the link. Okay, I'll share that. There is a playlist with all the lectures and all the online sessions. I'll do that. Okay, so let me write it down. Picture, link. Hold on. I'm writing down it in Russian. That my brain is switching. In Russian, take a picture of the whiteboard will be сфоткать доску. And I was thinking for a couple of seconds of how to call that properly. So yeah, there was a question about the potential energy. Let us observe the change in the potential energy of this particle, of this pendulum, as the angle is changing. So we're interested in the movement of the particle in the y direction. And if the angle is at 0, our y coordinate, we can say that it's, well, okay, we can say that it's 0 as well here. We can sorry. So 0 of y will be here. The point is here. So if the angle is 0, y is equal to 0. And if theta is not 0, we're going to have the following. So this L is not changing. This thing over here, this one, is the L times cosine theta. And in the y direction, this difference, I'm going to show it in red, this one. This small difference is equal to L minus L cosine theta, or L1 minus cosine theta. Maybe I'm slightly over complicating stuff. Okay, but if we just assume the 0 of y to be here, the height will be just negative L times cosine. Did it become any clearer, or I'm confusing you?
Yes, actually, I just remembered how to do it. Yeah.
Okay. So yeah, I'm writing it in this form without any additional constants because it's just
Yeah, yeah.
simpler. We can skip that. We can say that
You
0 is
can just
here and here's just minus cosine. So
yeah,
yeah.
yeah, yeah,
Mhm.
yeah. Okay, got it, got it. Thank you.
Yeah, sure, no problem. So this is the assignment. There are two parts. Uh, yeah. The second is slightly longer and slightly more difficult, but you can just ask me on or ask anyone in the chat. I mean, you can ask each other basically because there is nothing,
Yeah,
no one no one else listening to this. But we can have a discussion. You can write me if something is not clear. I will cover that again. There's no problem with that. We will have to understand this whole thing anyways in order to properly control the robots. So let's do it.
let's do it. I think I'm gonna do uh the assignment given by uh why did I forget his name? Fedor, yeah,
Mhm. Yeah.
regarding the key point controller thing.
Yeah. So that approaching the control from a different side,
Yeah.
you're doing the open loop, but on a complicated system, and we are going to do closed loop, but on very simple systems. And
Mm-hmm.
eventually we'll converge from two different sides, and it will merge into a coherent picture at some point.
Okay, let's go.
Yeah. So thank you very much for coming. I
Yeah,
appreciate
thank you
that
too.
you found some time during this
Yeah,
period
sure.
of the year.
I always forgot about the meeting, and that your message always popped to my into the
Uh,
phone, and then oh, I need to to go to the meeting, and
uh,
yeah,
yeah,
it
got
always
it.
happens. So, but at least I attend. So
Yeah, right. So have a nice evening. See
you
you.
too.
Bye bye.
Thank you.
Thanks. Until next time.
Bye-bye. Yeah, see you
Bye.
soon.
Bye bye.